All right, welcome everyone. In today's lecture, we're actually going to go over training or learning model that we've created so far. Well, let me go ahead and share the link to today's lecture inside of the X-Ray channel. I saw yesterday there was a little bit of trouble finding which lecture we were actually covering, so I just shared it there on the channel so everybody has a link to it. Um, with that said, this is where we have currently stopped, right? We've created our neural network with, I believe what we decided to go with was 3 linear layers, where we would input 9 neurons. In this drawing, we're inputting 3 neurons. It is a fully connected function with weights and biases, where weights are defining how we communicate to the next to the output of the linear layer, and biases are deciding whether we should or we should not communicate to the output of the linear layer, right? So every weight inside of each neuron, so currently this neuron here, the weights would go and render whatever let's say the number 9 went in there. Well, the weights would alter the number 9 and change it into what should go into the next neuron, or what they think should be implemented into the next neuron. And then our biases would look at that number, look at the input from the other neurons and say, no, you know what? We probably shouldn't talk to them. Let's just keep this to ourselves. Or it would actually allow the communication to happen. So biases is how do we communicate to the next layer, whereas weights is how am I being implemented to myself to mutate and be transferred into the next layer, right? We covered how we would essentially funnel this information. If we take this entire drawing here and I group it because I don't want to lose it, and then I turn it this way, I see we have a hot mic. I'm just going to go ahead and mute that there. All right. And I turn it this way. We can see that this turns into a funnel, right? It's essentially just a funnel. I'm feeding information into this massive funnel. And this funnel is essentially working with all the information that I provided, squeezing it at the very end through the sigmoid function, and then allowing an output of a number between 0 and 1. And that's what returns to me my binary function. Right? So that's our model. After working with our model or creating our model, we took a look at our data from the water quality data. And let's go ahead and, excuse me, let's bring up that water quality data one more time. So here's our water quality data set that has a total of 9 attributes. We can come down, goes all the way to 9 for turbidity. And then finally, we have our actual Boolean value or our label, right? We have 9 features, and our label is whether the water is drinkable or not. And here in Kaggle, they do quite a bit for us as far as data goes. They show us an analytic for each individual column. When we came back to TLDraw, we talked about these analytics a bit as well, and how we should imagine data to be a flow, right, of it just being plotted. Now, we took into account things such as, well, what happens if all of a sudden I have a skewed value, right? Something that falls outside of my left and right lateral limits of what the normal input is for my data. Well, we determined that we would use either it's scaling and standardization. Right? And the way we would decide to use that is by either going with a min or max value, or we would determine what the mean is and exchange that, right? So here we would account for the absence of data or a skewed value of data to ensure that all of our data is falling within this flow and that our model can make accurate predictions. Finally, we talked about how we would divide our data. We take our file and we divide it into batches, right? One utilized for training and the other utilized for testing. All right. At this point, does anyone have any questions over the material that we've covered so far in theory? All right, we're looking at a quick overview here before we actually start writing some code. Let's hear it, Momo.
Yeah, I just want to know what the meaning of the weight. You give weight for what?
Sorry, could you say
In
that
the
one
neu-
more time?
in the neurons,
Uh-huh.
and the like, for example, the second the layer, the hidden layer.
Mm-hmm.
So you start giving weight. Is this weight for I don't understand the meaning, the physical meaning of giving weight. You're giving weight for what?
Got it. So we're not actually giving weight. I know when we think of weight, we think of quite literally something getting heavier, or is maybe something getting larger or denser, right? Weight is a
No,
math.
no, yeah. I'm sorry. Yeah,
Go
go
ahead.
ahead.
What was your
No,
question?
no, I know weight. You're giving the like the importance, right?
No,
Is not how much importance that affect.
no, that's
Okay,
not what the weight is. So the
okay.
weight here is an actual mathematical expression that will mutate the value of this neuron before running the math that happens under the hood to create the next neuron that's being outputted. So this is math that will apply to this neuron in order to affect this final one. Does that make sense, Momo? Of
Yeah, okay. Thank you.
course. All right, and I see a question from Rojan.
So I have a question on that though. So do we first initialize the weight ourselves and then it will take over on adjusting the weight later on? Or do we keep adjusting the weight until the training is done?
Yeah, that's a great question. So the moment that you write nn.linear and you initialize the class, that class is being initialized with attributes, right? So if I were to define this class, right, because linear or the linear layer is essentially just a class that we're inheriting, or excuse me, that we're utilizing composition for, it would look something like this, right? It would have its init value there, taken self, and from there, it would probably have something like self dot weights equal, and then it would have some sort of function here for or method, right? Where it would be self dot generate weights. And then same thing for self dot uh, biases. Where is it biases? It is biases. And then generate biases. Right? Now, when I use this class, when I establish it in my layer, I usually say, oh, well, this is just going to utilize, let's say layer one, it's just going to be the instance of a linear layer. And then here I also have to pass in input, or let's just say in and out. And it looks like in is a keyword, so in neurons and out neurons. Right, so when I initialize this layer, I would say 9 and 3. Right, this is all essentially it's happening under the hood. The moment I say, hey, layer 1 is being created this way, well, now it knows the number of neurons that it's going to accept is in neurons. The number of neurons that it's going to output is outward neurons. And then the self.weights and self.biases, I never pass in these attributes into the class itself. It just generates those weights and biases on its own at random, right? It doesn't do anything crazy to actually try to fix the problem or start from a good location for us to be able to find the correct answer, right? These are just generated at random. We ourselves during the training process are going to mutate these to update them and make sure that the linear layer is working correctly. Does that make sense, Urjan?
Yes, thank you.
Of course. Any other questions? Yeah, I'm actually going to comment that out just to ensure that it stays in our notes. All right, let's hear it, Tim.
I'm sorry, when you said linear 9-3 for the that goes all the way down to 1, or is that just, and that's shorthand for it, right? Or is it,
No,
am I
this is,
misreading it?
yes, this is just representing one linear layer. So this linear layer here that we're seeing in this example, if I were to
Yeah.
highlight it, right? This example would be something like 3 and 2, because we are taking in 3 neurons. Oh, hello. We are taking in 3 neurons, and we are outputting 2 neurons. Does that make sense, Tim?
No, yeah, okay. I was just like, so this is not representing what you wrote, basically.
No, we're not at the model portion yet.
Yeah. Just make sure.
Awesome. All right. So let's actually start writing our model and seeing some of the code that we've seen so far. As we know, repetition is key. So let's go ahead and start writing all of our imports here. So I'm going to go ahead and import torch, because I'm going to need PyTorch. I'm going to say from torch, I want to import NN as NN. I am going to also import Tensor. And I believe yesterday we also covered from torch dot utils dot data import. Oh, nope, we haven't covered that yet. Apologize. We need to import pandas as PD. And from sklearn, I'll have to look at the sklearn import here shortly. Let's make sure this works correctly so that I'm working in the correct virtual environment. Okay, everything there is working correctly. Now I'm going to go ahead and make my binary model that will take in 9 features and have a total of 3 layers, right? So let's go ahead and write some pseudocode here. Takes in 9 features. Has 3 layers. And utilizes the sigmoid activation function. All right. So there's my class for binary model. How do I actually write this class? All right, let's hear it, Gary.
So this is where you would have your definite.
Okay, let's go with my init method. What
Uh,
else?
Add a super.
Okay, I'm gonna go ahead and add a super.
All right. And then that's where you put your binary model itself. And then init.
I do have a question, Gary. So it looks like we're utilizing the super method, and usually the super method is utilized to initialize a class that's being inherited. But I don't think we're inheriting anything as of right now. Am I missing something?
No, that's typically what we did last time. But if you're just making a method out of it, then you can get rid of the init, right?
Yeah, we could. But we actually do have to inherit something. Let me see. Do you want to phone a friend?
Yeah, go ahead, Momo.
Yeah, the neural network module.
Yeah, we
And yeah,
need
will
nn dot
inherit from.
module. That's right. So nn dot module is inherited. We have our init. Okay, good. So now we have a model. We have our init. What are the layers going to look like, or what are my attributes? Let's hear it, Tim.
So there looks like there's 2 layers. So self dot linear 1 equals, and then dot linear. Oh wait, we have 3 layers, so yeah, but it's 9. What would 7? What was,
Yeah, we could go with 7. 7 works.
okay. And then 2, yeah. 7, 4. Yeah, same thing, 7, 4, and then down to 4, 1. And then, do you have to import a sigmoid
It comes
for
from
active?
NN as well.
Okay, so then, yeah, self dot activation equals NN sigmoid. Just parentheses.
Great.
And then, yeah,
Awesome. So there you go. We have all of our layers defined, right? We're able to take in 9 neurons and we're slowly funneling down to one final neuron, which then gets passed to my activation function. But as of right now, I don't have any passing. And I see something from Brandon. Go ahead.
Yeah, so when I was playing around with this very little yesterday, I tried changing the numbers around for the input output of the nn.linear function. And I tried to like change the rate at which we decreased. And I ran into some issues doing so.
Change the rate at which you decrease. You mean the numbers
Like-
at which you decreased?
Yeah, like 9 to 6, and then 6 to 3, and then 3 to 1. And it like threw an error. Is that expected? Or I could probably just come to you later about it.
Yeah, that sounds like a syntax error somewhere. That should have worked. Yeah.
Okay. Thanks.
All right, of course. All right. Well, now we've established all of our layers or all of our attributes that belong to this model. But we haven't implemented the passing of data through all of these layers. How do I do that? All right, let's hear it, Erjan.
Create a function forward
Yeah, so I would have my forward method.
that takes in a self and an x.
Okay.
And then we can make x equals to self that linear 1 parentheses x. And then we can just copy and paste that to 3 more times. Change the 1 to 2 and 3.
Sorry. My copy and pasting skills are not the best, which is, I need to fix that. All right. Okay, so there's our forward pass. We're passing it through all of our linear layers. What about our activation function?
No, we just call the self that activation and put x in there. And then return the x.
Nice. So we're using variable reassignment, but we're essentially just passing whatever tensor or parameter gets put through our forward pass and feeding it down each independent layer all the way to my activation function and returning the final output. This is great. I have my model. And now how do I create an instance of this model? Because currently this is just a class. Let's hear it, Gary.
You can set it equal to model. So model equals your binary model function.
Yeah, model equals my binary model function. And now when I run this, we'll see that it works correctly. I have my model has been created. This is good. I have now created my model. Now we're going to go into the data portion. Due to time constraints, I'm going to actually take over at this point and get all of our data. Excuse me, ready to go. I'm going to go ahead and start a variable named data. I'm going to utilize pandas to read my CSV file. Which in this case, I actually don't have one. So I need to cp-r from 3 resources into resources. All right, let's see if that worked. There's resources and there it is. All right, so now I have my data. So now I'm gonna read CSV, pass in the path here, which is to resources / water potability .csv. All right, so that's gonna allow me to read my data. From there, we know that I want to change the null values within my data, and I want to make sure that that gets filled. So I'm going to go ahead and do that with data.fill, and I want to fill it with the mean. And this is where we are essentially analyzing our data flow that we talked about down here. And we are accounting for missing data, right? We're not necessarily squeezing our data so that it falls into the funnel like we want to. Right now, we're accounting for missing data. So that's going to account for missing data by filling in each missing null value. From there, I want to separate my data into both features. And I want to have my labels. Right, so in my features, I want all the columns with the exception of potability. And in my labels, which are my answers, I only want the potability column. Good. So now that I have this information, I can actually start working with sklearn to start standardizing and scaling my data. And I'm going to go up above to fix my import statements here. So I'm going to go ahead and say from sklearn dot preprocessing, I want to import standard scalar. All right, so there's my tool. Let me run this again so that I have it. And I know there's going to be another import from sklearn, so I'm just going to bring it in now and say from sklearn dot model selection, I want to import train test split. I'm going to execute this block of code so that I actually have these import statements. Then I could utilize them. All right, so I'm going to standardize and scale my data by utilizing the instance of standard scalar. I am going to then scale my features. I'm going to pass that into scalar.fit transform and features. So that's going to both standardize and scale my data. Now my features are fixed. My my labels are created. Well, let's go into creating my training split now, right, which is the final portion here. I'm going to go ahead and pass in. Let's see. I'm going to go ahead and grab my information. So I'm going to say, hey, training features, which is what comes back first. Then I have my testing features. I have my training labels and my testing labels. I see there's a question. Give me a second here. All right, this is going to take in my features as my first argument. It is then going to take in my labels as the second argument. And then finally, it wants to know what the training size will be. Well, I know that for my training size, I want 20%, so I'm going to pass in 0.2. And I believe that is everything that we need here. I am then going to utilize variable reassignment to pass this into tensors. And yep, there you go. So I'm going to pass this into a tensor. I'm going to pass in training features, and I'm going to ensure that the data type is of torch.float32. I'm going to do that for each one of them. So here's my training features. I'm going to change that for my training labels. And I'm then going to change that for my testing features. And my testing labels. Okay, great. I'm going to try to execute this block of code. As expected, I do have an error. Could not determine the shape of object type series. All right, so where is that coming from? It's telling me that that's happening at testing labels. Oh, go ahead, Erjan.
I encountered this one yesterday, and I think it's because of the labels needs to be reshaped to 9 features.
I don't think it's about the 9 features per se, because the label is supposed to be 1, but you're definitely right. It does need to be resized. And let me go back to the curriculum here where it will tell me how to do that. So there you go. All right, so for my labels, I need to utilize the attribute dot values. So let me implement that in both tensors here and try to implement this application now. And now we see that it works. All right, I'm grabbing the values of this data frame because as we know, our training labels is not a numpy array yet. So we need to grab dot values. Oh, excuse me, it is a numpy array. We need to grab dot values so that I can churn it into a tensor without trying to nest it. And then we have our training features, which are already a numpy array and don't need much manipulating. All right, so just quick recap of everything we've done so far. We've imported everything we need to be able to create our model. We created our binary model with the forward pass, made an instance of said model. We then grabbed our data, accounted for missing values. We separated our data into features and labels. We standardize and scaled all of our features, which is essentially this implementation that we see here. And then we split them so that we have training features, testing features, training labels, and testing labels for our data to be both tested and trained. All right, at this point, does anyone have any questions over what we've done up to this point? Let's hear it, Gary.
What are the values that you're getting out of potability?
So potability is a 0 or a 1. Are you talking about this dot values here?
Yes.
Got it. So if we go ahead and print training labels and we pass this through the code editor, we'll see that the training labels is a data frame of integer 64, right? Well, I don't want to pass that into a tensor because the tensor won't be able to turn that into or it won't be able to cast it into a tensor. So by passing in dot values and then putting it in, now we get a massive array of numbers that could be turned into tensors. Does that answer your question, Gary?
Yes, thank you.
Of course. All right, so let me take that off there so that we don't have that noise. Great, so let me go ahead and do that note here. Manipulating data, and actually this should be pre-processing data. And here we have creating our all right, so our model has been created. We have pre-processed our data, and now we're ready to move into the next step when it comes to our data. So yesterday we went through the entire process of cleaning up our data, but even though we cleaned up our data, it's not in the correct format to actually be fed through our tensors or through our model in order to be trained. So the next thing we're going to talk about is creating data loaders, all right, which do exactly what they are called. Their entire purpose is to feed the model tensors and provide labels for evaluation both during testing and training process. Well, good. That's great to know. I understand the purpose of a data loader now. Let's take a look at my hidden layer, my activation function here. And let's back up a step. All right. My data loader is going to work in the background over here. And I'm just going to go ahead and put DL for this, make it extra large so we could all see it. So my data loader is going to work right before anything gets fed into my model. And this input that we see here, whoa. Oh, Jesus. Let me try that one more time here. My TL draw skills are getting put to the test. Okay. They were put to the test and I failed. There you go. Now this input here is going to actually belong to our data loader. And for every single one of these rows, my data loader is also going to have its corresponding labels. Right? It would have either a 0 point, it could have a 1 point, or again, a 0 point. Right? Just like we have 3 separate tensors that we're feeding through our neural network, it would have 3 separate labels. And this would all belong to the data loader. Well, the data loader, when it gets implemented, it would feed this tensor into the model. And for us, it would also give us a way to reference this tensor at the very end of our model to say, hey, did this work, right? Is this the correct output that I expected? Or is this totally off? Okay. Now, our data loader is going to serve a little bit more, it does a little bit more functionality, and we'll go over that here shortly. But again, its entire purpose is to provide us both the labels, which is the answer, and the features, which is what gets fed through our neural network. So that when we're training our model, we can grab the output of the model and compare it to its corresponding label. So let's take a look at here. Let's start writing some code. I'm going to now import, excuse me, from torch.utils.data two separate classes, one named data loader and one named tensor dataset. We haven't talked about tensor dataset yet, but we will here shortly, right? For our tensor dataset, we have all of our tensors up above, but they are not connected yet. They're not stacked on top of each other, right? So in order to stack them or to connect these two, because currently my features and my labels are separated, I need them to be next to each other and coordinated to one another. I need to place them inside something called a tensor dataset. Now, what a tensor dataset is going to do, or what it's going to create, is that it's essentially going to create a stack that looks like this, where it's going to have labels and it's going to have features. And let me actually minimize this a little bit and zoom in. And it's going to then stack them on top of one another and so on, so that they are iterable, right? For every index, there's going to be both features and labels. And wow, I got these backwards. Where labels is only of one. So that we can iterate through it or feed it to something that will iterate through the stack and continuously feed our labels and features. Well, let's put that into implementation here. I need a training data set that will take in a tensor data set. And this tensor data set will have my training features and my training labels. All right, that's it. Nothing more than that. I'm passing in both the labels and the features. And I need a testing data set, which will be, again, a tensor data set that takes in my testing features and my testing labels. All right. Well, let's take a look at what that looks like now. We can go ahead and print, and let's go with testing because that should be considerably shorter. And let's go with dataset. Well, now if I try to print tensor dataset, this is just pointing me towards the instance of a class. All right. And right now, the instance of the class, what it actually holds inside is you could think about it as an array of arrays, right? If I were to write this in Python code, this would look as such. It would have an array, which would then have labels and features. So I'm just going to put FT for. Right, that's all we're creating. We're creating a data structure that it has an array of arrays. But there's no iterability being implemented just yet. Right now, we just created the data structure of a nested arrays. Well, we talked about the function data loader that is going to be in charge of feeding data into my model. So this is where we would implement our data loader and what brings in the actual iteration process. So we'll say my training loader is data loader that takes in my training data set, and it has a batch size, and we'll cover these attributes here shortly, and we'll go with shuffle being true. All right, so my training data loader, it's taken in the training data set, which is our iterable stack that we just created. Then I have this batch size here. Well, what does batch size mean? It's just saying, hey, every time you provide data to the model, I want you to provide a size of 32 nested arrays in total. So if this was Python code, again, I could say data loader make equals, and down below, if I do what is the length of data loader every time it is fed into my model, well, I would see 32. There would be a total of 32 nested arrays within it, right? Or nested lists within it. Now, 32 is kind of the standard as to where you should start off with. But your batch size is very important when it comes to training. And we'll be taking a look at that shortly as to how it affects our training. The larger the batch size, the quicker your training loop is going to end, but it's not going to actually help your model, right? So you'll become more efficient at your training loop as to this is when I started training and this is when I finished training, but you'll become less efficient at the act of your model learning. You could start and end training without your model actually learning or being done with the training process. It could still need more adjustments. So you want to stick to lower numbers, right? I would suggest that you don't go above batch sizes of 32. You definitely can. There are cases for it. And this is kind of where we venture into the realm of you got to play around with it. You don't really know off the top, but try to stick with lower than 32 and something divisible by 2. And as far as something divisible by 2, it's easier for machines to actually work with pairs of 2. So you want to provide something that's actually divisible by 2. You can try something that's odd, but you could run into some unexpected behavior if you do that. All right. So I'm passing in my data set. I want to pass 32 batches or 32 samples at a time. And then I'm saying this shuffle equals true. Why would the shuffle equals true be important? Well, we talked about oh, I saw a hand go up.
I was just going to take a guess, but you were going to explain it. Never mind.
Oh, awesome. Yeah, we talked about how the model could possibly memorize information if things are being taught the same exact way over and over again. Well, this shuffle equals true is ensuring that data isn't being fed in the same exact pattern or in the same exact order into our model, so that it's receiving information in different ways. Now, if we talk about this in a mathematical perspective, weights and biases need to be able to adjust correctly. And if I'm feeding it the same exact pattern every single time during the training process, well, that math is eventually going to be adjusted and provide good results for only that pattern. So I need to shuffle the information so that it can become more responsive and adaptive. All right. And that's our training data loader. I'm going to quickly make our testing data loader, and then I'll open up for questions. So here's our testing loader. It's going to be a data loader that takes in the testing data set. Again, it will be a batch size of 32, and we'll play around with this later. And there's going to be the key difference here, where I'm going to say shuffle equals false. Right? Whenever I'm evaluating my my model, I actually don't want to shuffle the data. I want to make sure there's some consistency so that I know how my model is performing. And I can determine which one of these batches within batch size 32 or which one of these samples within the batch is actually causing some weird functionality. So I could go back and adjust layers if I wanted to myself. All right. Now, more importantly, as we'll see later on, the adjusting of weights and biases will only happen during the training process, and it will only happen with training data. Once we start testing or evaluating our model, we're no longer updating those weights and biases. We are simply looking at the performance of our model at that current state, and then evaluating if it's accurate enough or accurate to the point where we feel like it's acceptable, or if we want to adjust it. All right, so there's our training and testing data loader with the one key difference of shuffle being true for training and shuffle being false for evaluating. Excuse me, everyone. I'm so sorry. Does anyone have any questions? Go ahead, Gary.
Can I just see a print statement from the stack you made? I just kind of want to visually see what's happening.
Sorry, you said you wanted to see a print statement from what?
The stack data from the training data set.
Yeah, that's this print statement here. It's not going to show you the actual value. It's only showing you the instance of the class. To reference back to OOP, this essentially doesn't have some sort of dunder method or representation method.
Okay.
But I drew it out right here. This is essentially what it would return.
Okay, thank you.
Of course, I apologize. I'm dying over here for some reason. Any other questions? All
I
right.
actually have a question. So when you say batch size up, is it up to 32 or it's going to be 32?
Yeah, that's a good question. It's going to be up to 32, not it will be 32. There will come at some point, maybe your data is not divisible by 32. So what it will do is it will not allow the batch sizes to go any higher than 32, but it will accept lower batches. Does that answer
Thank
your
you.
question, Tim?
Yeah, thank you.
All right. Awesome. We've been going on for quite a while now. Let's go ahead and take a 15-minute break. Currently right now, and let's just call it a solid 13. Currently right now it is 9:52. let's come back at 10:05 and continue on with our lecture. Thank you so much, everyone. Doing more recording. Welcome back, everyone. Before we left for our break, we talked about data loaders and the data sets. We went through creating a data set, and now we've created a data loader, which is just going to feed us batches of said data set, shuffled along with the features corresponding to each one of them. All right, so that we can actually go through the process of training our model. Well, now let's talk about the training loop. And the training loop is actually a lot less sophisticated than what we thought it would be. Or you may think it is, right? I was definitely surprised when I saw what the training loop actually looked like. Essentially, what our training loop looks like is, let me back up here. Our training loop takes in our model, right? And all it's going to do is it's going to recycle this information over and over again. So it's going to, one, feed data from the start of our data loader all the way to the end. So here's the first portion of the loop, right? There will be an evaluation here at the end where I'm going to calculate my function, where I'm going to say, hey, my loss, excuse me, is equal to my label minus the output, right? So that's just going to tell me how far off am I from having a good, how far off am I from having a good answer, right? From having a good prediction. My model's making good predictions and I can stop training it. And then finally, we have the back propagation function, which is the last part of my training loop here, right? Where the back propagation doesn't necessarily impact my data loader. Instead, back propagation is going to go backwards, right? Not necessarily towards each point here, but it's going to go to each linear layer and affect the weights and biases of each one of these layers for us. So it's going to, one, grab my loss function, right? It's going to say, oh, well, this is how far off we are from being true. And then it's going to run some math running backwards. We're not going to see it. We're not going to manipulate it. It's all going to happen between the back propagation step. We don't have any control over it. And it's going to work backwards and talk to each linear layer or each neuron's weights and biases and say, hey, this is what I need you to change, starting from the very last neuron and working backwards. Right? It's going to talk to the weights and biases here, find out how it could change its output so that it would be closer to the correct label, and then work a step back so that it can populate these weights and biases, and so on. Right? It's just working backwards to ensure that this funnel is actually working correctly and funneling data so that we can get the expected answer, right? That's all that my training loop is doing. It's going to feed data, calculate the loss, and then from there, use back propagation to update each one of my weights and biases. Does anyone have any questions over that? How the training loop works or what it's going to look like here shortly? All right, let's go into it then. So here we're going to go ahead and start our training loop. And typically when you go through a training loop, it's going to look like a nested for loop, right? I'm going to say for epoch in range, and say, let's do range 100 right now, which is just how many times the model is going to go through the training process. And then finally, I'm just going to say, well, now that I am nested inside this training process, or how many times I want to actually train my model, let's say for features and labels in my training loader. All right, so remember my training loader is going to return a batch of 32. All right, and if we take a look at our drawing that we did down here, it's going to return a batch of 32. And I'm just utilizing the spread operator here. I'm grabbing labels. All right. And I apologize, things is destructuring. I'm grabbing features and I'm grabbing labels straight out from that nested array that the training loader is going to provide. So it's providing me 32 shuffled samples. I am destructuring it so that I have both my features and labels easily accessible. And now I'm going to start feeding it through my model and say, hey, well, here's my output. I'm going to feed it to my model by passing in my features. Then I'm going to print my output. All right, for now, for simplicity's sake, I'm going to go with 10 so that we could see it. So we'll see a massive amount. Remember, there's 32. Let me see if I could. Let's just do range 1 so that we could see it happening one time. All right, there would be 32 outputs, and this is the guesses that it made for those 32 samples. All right, these are all the samples that we fed it, 32, and these are all the accurate guesses that it was able to make once it reached its sigmoid function. Does anyone have any questions regarding this structure up to this point? Let's hear it, Brandon.
Yeah, could you scroll down the tensor list real quick?
Mm-hmm.
Okay.
All right. Tim?
Is there a already set bias or for anything just in place for tensors?
Yes, the moment we created them, they already have their, not the tensor itself, but the linear layer has weights and biases already being applied.
But is it always skewed in one way just because you made it, is what I'm asking? Or is it 50-50 right away?
Got it. So the bias, I know that when we hear the term biases, that's what we think about, right? If something is being biased. Is it going left or right, or is it leaning towards one side or the other? In this case, the bias isn't really functioning that way. Instead, is interpreting whether we should speak or not speak to the next function. And that kind of depends on what the weights are being determined to. So it's more of a reactive functionality in that case.
Mm.
Does that make sense?
Yeah, that makes, you just opened my eyes. Thank you.
Of course. All right. So now here's our current training loop, but it's missing a couple of things, right? One, I need to figure out how I can calculate the loss. And in this case, what we're working with is a binary classification model. So if we are working with a binary classification model, well, we would want something that gives us a function for backpropagation that works with something related to binary classes, right? And in this case, what we're looking at is binary cross entropy loss. That is going to be our loss function. And what binary cross entropy loss is, it's just a good way to analyze and compare whether something, we're going to be passing the value of 1, and we're going to be passing the value of 0.44, right? That's, so my label would be 1, and then the output of my function would be 0.44. It's not as simple as I wrote it down here, right? I can't just subtract them from one another and say, oh, well, 0.6 is what needs to be updated. And then from there, it would go backwards and update everything so that we have the 0.6. It needs to run quite a bit of calculations to figure out what the actual loss would be, because we're looking at probability between 0 and 1. So it has to run that under the hood. And then it also has to have a backpropagation function to talk to each layer's parameters and update them. Well, this comes built in with PyTorch, where we can specify, hey, I want my criterion, which is the typical terminology utilized for loss functions, to be BCELoss, right? Binary cross entropy loss. I want to know how far off I am between the correct guess, 0 and 1, and I want to utilize a backpropagation to be able to work to talk to this model. Now, oh, go ahead, Tim.
Yeah, sorry about the noise, but instead of criterion, why is it not just called loss or something like that? Why do you call it criterion even though you're using BCE loss? It's my question.
Yeah, so loss could be a key word. Loss is also utilized in machine learning as parameters in other functions. So it likely it tries to keep that separate as a keyword. And then also criterion, well, what I'm doing is I'm critiquing my model, right? I'm trying to figure out how far off I am. Does that make sense to me?
Yes, thank you so much.
Of course. All right. So now I have my criterion. I have my BCE loss. But there's a little bit more of a complicated process when we're trying to not only find the optimal minimum, but we're trying to update information, right? Currently, the part that we looked at is updating information. Well, I don't want to update information at random or to just continuously update them depending on loss, right? When we go and we plot our model, there was a very good image that Erica showed us, which unfortunately I don't have available to me. But essentially, our models, the way they learn is they learn in a parabola function. So it would look something where we have our x and y axes. And when this gets drawn out, our parabola would look, oh, hello. Our parabola would look something like this, right? Well, let me draw out the parabolas that we're used to seeing, or that everybody may be something more familiar with, right? This is what people may be more familiar with, and this would be something simple to work with because we could easily identify, oh, hey, this right here is the bottom. This is where I want to be located. This is my optimal learning capacity, or where my model should be learning or will learn at its best. Well, in this case, our learning models don't actually have this sort of curve, right? That would be too easy. Instead, our learning models have a curve that looks something like this, where things are just kind of all over the place, and maybe there's a spike, and then it goes on, right? And who knows, maybe this spike goes all the way up there, maybe it stops up here, and then comes back down and continues. Not the best parabola that I could possibly draw. Maybe I could back that up. Let's try to do that a little better here.
As you're drawing that, is this like how sound processing works? Kinda?
No.
No, they don't do this like with waves to
There
make
is.
it.
Oh, go ahead.
Nope, you're good.
Yeah, there is waves in there as well. I'm not exactly sure as to how it's being interpreted with sound, like a system that would turn sound into text. Not exactly sure how that works. Uh, but currently what I'm depicting here is the learning model's process of how it would identify.
I was
how to-
thinking like Google Translate. How would you make this more interpretive for the computer to learn? That's what I was thinking.
Right. Okay. So currently, right now what we're going through is we have this weird looking parabola that we want to learn from. And we want to find something called the optimal minimum, right? The lowest point in the entire learning process, where our loss is the lowest and our model is the most efficient. Well, we have to find a way to manage how this loss function is working and tell the loss function to calculate information, preferably at the optimal minimum, right? Well, how could we do that? At this point, what we're going to start talking about is something called an optimizer. And optimizers don't necessarily, how do I explain this? A good way to think about this, as I'm sure everybody can probably relate to, or I guess let me try to explain this exercise, right? You're learning how to navigate through the woods with good old map and a compass, and you need a way to measure your distance. Well, typically, in order to learn how to measure your distance, is you would set out some sort of course where you would have flat ground of, let's say, 100 yards or 100 meters or whatever metric you would like to utilize. And from there, you would start from one point of the course, move over to the secondary point. All right. So you start from one point, move over to secondary point, and you tell yourself, oh, well, I need to take a total of 122 steps in order to cover 100 meters. Right. Well, our optimizer needs something that's pretty similar to this analogy, right? Our optimizer needs to know, well, at what rate is it that I'm supposed to take a step at? So after a training process is over and I've made a loss calculation, well, if I made that loss calculation, how far do you want me to go? All right. So we start our initial step there. And I tell it, hey, I want you to take a total of one step. Well, it takes one step and then it stops here. Right. And this distance here would then be the dictated distance. It takes one step. Well, now it falls all the way down here. And it could think, oh, well, maybe this is the value, the optimal minimal value. All right. But it could be wrong. Maybe I don't want it to stop there. Well, I tell it to take one single step again. And when it takes one single step, it's now stuck. There's an uphill. So it says, oh, well, I can't go that way anymore. And then it falls back one single step. And then we see this bouncing back and forth over and over again, but it's in the wrong minimum. Right? So there's my learning rate kind of explained here. Well, essentially what we're trying to do, if we were to go back to our example of learning how to navigate with a good old map and compass, is we have to account for terrain, right? We have to know how to handle if maybe these 100 meters are not uphill, or excuse me, are not flat. They're actually 100 meters at an inclination. Well, here, maybe I still take 122 steps, But rather than just taking 122 normal steps, I know I also need to put some sort of force. Maybe it's like half of what my regular force would be to take a step. Right? I am building momentum to climb this hill. All right. So at this point, what my learning rate would do is, hey, I want you to take a step. Goes through the process one more time, takes one single step, and it falls here. All right, take a step again. Takes one single step and falls here. And now, because I gave it momentum, I say, hey, take another step. Well, it takes a step and falls here, just like we saw before. But rather than falling back and bouncing back and forth, it would utilize that momentum to take a next step and fall on the other side of the curve. All right, so that's how our learning rate and momentums would be implemented as far as our learning rate goes. Does anyone have any questions over learning rates and momentums? Let's hear it, Gary.
What determines how much momentum you have? Like maybe I think you just give it a general gist. Maybe you'll get more into it. But
Yeah, these are actually parameters that you can specify to your optimizer and tell it how it is that you want it to learn. And this is where more of the experimental part comes in, where you want to try and see how it goes, right? You want to give it some sort of learning rate to start off with, which typically the standard learning rate is of 0.01. And the standard momentum, and correct me if I'm wrong, Erica, here, because I don't remember momentum off the top of my head, is 0.05. All right. So it would go through this process of trying to build it with the standard values if you don't provide it. And there's a way where you can get this auto plot. We're not going to be covering matplot and doing all these visual graphics because due to the time constraint that we have in the program. But you could definitely look into how you can plot this information so that you can have more of a visual aspect as to where your learning rate is falling, and if you need to give it more momentum in order to find the optimal minimum. Does that answer your question, Gary?
yes, thank you.
Of course. All right. Now, this is all great information. We've understood how learning rate and momentums work. But now let's go into a little bit of implementation, right? There is two types of standard learning rates that you'll see typically in machine learning or in deep learning. One of them is called SGD, which stands for stochastic, I'm probably wrong, gradient descent. And what this is doing is exactly what we mentioned. Right, we would specify a learning rate and a momentum in order to try to help this optimizer find the correct or the most optimal, the optimal minimum within our learning parabola, right? Now, SGD is great and it can still be implemented for most models, but there has been a new optimizer that is hitting that is becoming common practice to utilize, and this is called Atom. All right, not our instructor, not our TA, but an optimizer named Atom. And Atom's means benefit is one, you does not take the argument of momentum, and you could give it the learning rate of standard 0.1. And what Atom does is Atom has been doing land navigation for a considerable amount of time, and he could visually see, depending on objects, whether there's some sort of inclination and how far exactly 100 meters is. So Atom, whenever he takes a step and he stops, he takes a look around him, sees, oh, well, 100 meters would be about right here, and takes a step, right? And Adam stops here. And now he sees that there's a hill. Well, there's a hill there, and he knows that 100 meters would be past that hill. So what Adam is going to do is, without me specifying, Adam is going to build the momentum it needs to be able to pass this parabola and fall on the other side of the hill. All right. And Adam will then take 100, so on. And from here, Adam will see that there is a huge decline that was lower than the one before. All right. And Adam may try to fall into that decline. Adam is a more responsive and adaptive optimizer. And because of that, it's become more of a standard to utilize Adam for your optimizer rather than a stochastic gradient descent. All right, so we'll be implementing Adam today. And I see Erica on the chat saying that she has shared a couple of videos. There's definitely a lot of good links being shared by Erica here on the X-Ray Questions channel. So please, if you have time, go ahead and take a look at that. All right, great. Well, now we have our information cleared up. We see that we can adapt our learning rate over each iteration so that we can find our optimal minimum. Well, let's go into implementing this information. All right, I'm going to say from torch.optim, which stands for optimizers, I want to import Adam. And let's just do from torch import optim, since we're likely going to utilize that later on. And now I can say optimizer is equal to optim dot Adam. So now I have my optimizer and I have my criterion. But we talked about this parabola, right? Where's this parabola necessarily being formed from? Right? How does Adam know what terrain he's going to be going through in order to find an optimal minimum? Well, we just pass in our models dot parameters into Adam. And what Adam is going to do is, we know model dot parameters returns weights and biases. It's going to plot our weights and biases in order to see what the terrain looks like, right? Kind of like grabbing a map and finding the grid square that he's going to be looking at in order to find his optimal minimum or the valley that he's trying to reach. And from there, he's going to start planning his route, starting off with the standard learning rate of 0.01. And we'll play around with this learning rate so that we can see the differences as to what it's doing here shortly. All right. At this point, does anyone have any questions over criterion or the Adam optimizer? Okay. It doesn't look like there are any questions. So let's move into actually writing some code here. We have our Adam optimizer. We pass in our model parameters. So Adam knows the terrains that he's going to be going through. We have our learning rate. So we know how far of a step Adam is going to be taking every time he needs to learn. And then we have our criterion, which is going to give us the back propagation step to be able to update the weights and biases at each individual point. All right, so it kind of works together as in Adam takes a step, right? But then criterion goes through the weights and biases and changes the terrain that Adam is going to be maneuvering through. So Adam has to be extremely responsive in order to be able to find that optimal minimum. So let's put this into implementation here. Well, first of all, we have to ensure before Excuse me, everyone. All right. So now, before we even start going through the training process, I want to ensure that my model is in training mode. This is going to tell my model, hey, I want you to train. We're going to learn now. I want you to consistently update those weights and biases and accept the criterion's backpropagation step. Well, how do I apply this optimizer and criterion? Well, first, within my training loader, the first thing that I'm going to tell it is, hey, optimizer, I want you to start from point 0. So when it starts making this learning rate, I want you to start as if you were from the very beginning before you try to find the optimal minimum each iteration. Good. Now, I already have my output, but I can now calculate my loss, right? And I want to calculate my loss utilizing criterion, and I'm going to pass my output and my labels that we grab. Labels is coming in from the training loader. Features from the training loader were fed into my model to generate an output. And now I calculate my loss. Well, now that I have my loss, I can go and implement the backpropagation step. And to implement that backpropagation step, all I need to say or state is loss dot backward. And that is going to go back and update each one of the weights and biases. And then finally, I tell my optimizer, hey, now that we're done with this process and we've updated, I want you to take a step forward. And then it takes a step forward without any sort of biases from the step that it had before and continues moving through this terrain in order to find the optimal minimum. Well, now let's go ahead and take a look at our loss function and how this is being applied here. And I want this inside the number of epochs. Here you go. Let's see. Oh, I apologize. I'm gonna make a num of epochs variable here just so that we can easily manipulate it. I'm gonna do 10 for this go around. And this is what we're gonna be iterating through. All right, so we're gonna be iterating 10 times, excuse me. And I'm going to print the epoch state that I'm currently at, the number of epochs total, and what my loss looks like, right? How far off I am for this training iteration. All right, let's go ahead and run this block of code. Looks like we got an error, which is okay. Criterion, which takes in output and labels. And target size 32, that is different to input size. Interesting. Not sure where this error is coming from, since it should be up to scale. It doesn't help that I'm dying from this cough. All right, welcome back, everyone. Let's go ahead and continue on our lecture. Right before we left, we got this weird error telling us, hey, you're trying to work with something of size 32 that is different than the input size. Something you need to fix this, right? The main thing that I got out of this was that there was a problem with my dimensions because it's telling me that this is in reference to size. And it also tells me that it's happening on my criterion function. So the only difference that I see here as far as criterion, because I know output is not my error, is my labels. So I need to adjust my labels so that they fit properly. So what I'm going to do is I'm going to grab my label and nest it within a parent tensor by utilizing dot view with -1 and 1. Now I could actually see my loss functionality working here. But look at that. Here we go. Here's my tensor working with Optim. It is inside of a training mode. Here's my number of epochs. I'm currently iterating through 10 epochs. And here is my optimizer taken into effect, working with criterion. So let's look at our loss function, right? So it starts off, and it's not always just going to be, when everybody thinks about how your model should be trained, everybody is always ambition in the idea that, oh, well, if I am training my model, well, that means that it should always be in a downward spiral, right? Or that my loss should always be going down. And people become really frustrated when they noticed that that is not the case. Your loss function will not always just continuously go down. This is not a good representation of loss. Well, you should think about loss, because remember, our optimizer and our criterion are working together to, one, define this parabola, and two, try to find the optimal minimum. So it would be realistic to expect a consistent downward flow in your loss. Instead, your loss may look something like this, where it's more of a function, then all of a sudden it continuously goes down, and then boom, there's a spike, and then it comes back down and continues to work. Your loss is more of a squiggle, but if you zoom out and try to look at the overarching picture from a very, very far away viewpoint, you'll see that in fact you do still have a downward spiral, right? Or a downward motion happening for your loss. It's just not as clean as we wish it would be. All right. So now let's take a look at our loss being implemented here inside of my training loop. Well, my loss is being implemented. It's going through. I have 0.70, 0.71. Then my loss comes all the way down to 0.60. Nice. Then 0.58. This is actually really good for a very first iteration to come all the way down to the 5s. Now we're at 0.6, and then all of a sudden we get that spike. Notice we went from 0.58, you went up a little bit to 0.64, and boom, there's a spike that goes all the way back up to 75. That spike is sustained, and then it falls all the way right back down to 0.6. And by the end of 10 epochs, we have 0.48 as our lowest epoch value, right? So let's try to manipulate this a little bit. Let's see what happens if I run up to 20 epochs and I change my batch size to be from 32 to 16. I'm gonna make sure that my batch sizes are being updated. I'm actually gonna restart my kernel to ensure that my model is starting fresh. I'm gonna execute all. All right, so there we can see our number of epochs being executed. Started from 0.67. There's a spike where it goes up to 7.9. And then we see that downward flow between 6. Again, we hit 5. This time we didn't actually go all the way down to the 0.4s, but we did stop at a 0.63 in this iteration of epochs. Right? Usually 20 or 10 is not going to be enough to train your model. You'll see this loss functionality, and just do not expect a continuous downward flow. All right, and let's open it up for questions. Brandon?
So when I'm reading this, my brain's going to a loss of like 0.67, so 67%. That seems like a pretty high loss. So am I reading this incorrectly, or is it really just that inaccurate?
Yeah, that's a great question. So this isn't in reference to percentage yet. We're not determining how often my model is actually correct or wrong. Right now, what I'm determining is how far away from being in the correct answer if my model is right now, right? Because currently, if my model guesses 0.57, right? Technically, that is correct, right? When I evaluate that, it is closest to 1. So if I run it against the label of 1 or true, it would come out to be a correct answer, right? But currently 0.57 is not the same thing as 1. So my loss function would say, hey, this is off by 0.50 something, right? And it's not a direct subtraction. There's a considerable amount of math happening under the hood as well. Does that make sense, Brandon?
I'm trying to understand it. But it's all good.
Okay. Yeah. Let me quickly write our evaluation process so that we could understand the difference here, right? So for our evaluation process, I'm actually going to bring in another third party here called Torch Metrics to bring in something called accuracy. So I'm going to say, oh, well, first I have to activate my virtual environment. All right, now that my virtual environment is activated, I can pip install Torch Metrics. And I'll share that here as well in the X-ray questions channel. Once you have Torch Metrics installed, well, we can bring in a class named accuracy. And this is what actually measures, hey, how often is my model correct, right? Well, I'm going to make an instance of the class accuracy. And this instance takes in one argument named task. What kind of model is it measuring accuracy for? Well, in our case, we can look at the top 3 options here. I am not working with a multi-classification model. I am working with a binary classification model. All right. So I want to measure how accurate my model is. And then I'm going to place my model into evaluation and say, hey, with torch.nograd, this torch.nograd is essentially saying, I don't want any weights and biases to be updated. I don't want there to be an attempt to update anything. I don't need you to calculate any sort of gradients for any of my layers. I just simply want you to run this information through my model and give me its output. All right, so now with Torch Nograd, I want to iterate through features and labels, not of my training data, but of my testing. All right, so there I'm grabbing my testing loader. I take the output, which is equal to my model features. All right, I'm passing in my features. Then I'm taking in the prediction to be the output dot round. Because remember, we're grabbing between 0 and 1, right? So that's all I care about. I want this to round. If it's 0.5, it should go to 1. If it's anything below 0.5, it should go to 0. So I'm utilizing that round function to take the output of my model and round it. And then finally, I can say, well, I want my accuracy to be updated. And it's going to take in the prediction and my labels for this set. right? Now, why is it being passed into accuracy? Accuracy is doing some sort of math under the hood where it's essentially keeping a counter over how many times the prediction is matching the label. So it's matching the correct answer. And then it's also keeping counter of how many times it's updated. And at the end of it, it's just going to give us a sum divided by the length of the amount of labels and predictions that we have so that we can get a percentage. And that percentage will be interpreted like this. Let's say print an F string of accuracy, where we have accuracy dot compute dot item. All right, so compute returns some sort of object, and we only want to grab that item attribute of said object. Now, at the end of this process, I don't just want my model to stay in evaluation mode, so I'm going to ensure to place it back into training mode. So currently right now, I'm going to run my training loop here one more time. We can see that after running it through a secondary loop, my loss function is still pretty high, all the way up to a 0.67. But now let's see what happens when I run it through my accuracy. I get a runtime error because anything that can go wrong will go wrong. And let me take a look at where this is coming from. Predictions are expected to have the same shape. Oh, looks like it's the same issue. I'm going to go ahead and run this through a view of -1 and 1. All right, and there you go. So not bad for, I mean, I guess it would be expected for a binary classification model, right? It's only has two options between 0 and 1, and it looks like it's accurate 0.58% of the time. So 0.58% of the time, it can actually make a accurate prediction, and this is my current loss, right? My current loss is at 67. So that's how far off I am from being at the true state. And this is how often my model is actually correct. All right, let's open it up for questions. Go ahead, Brandon.
Wait, you're saying the current iteration of this model is only accurate 0.58% of the time, so less than a percent?
No, excuse me. I apologize. It's only correct 58% of the time.
Okay.
Yeah.
Actually, that leads me into my next question. Is this pretty typical for newer neural models?
Yeah, that's a great question. So keep in mind, we're starting off with brand new weights and biases, right? We didn't actually grab weights and biases from some sort of previous study or some sort of previous model. We're starting off with our own weights and biases that are being declared at random by the model. And we're trying to train it with a very limited amount of data, right? So yes, this is a very expected output. I don't think that this is something that's completely out of the ordinary, right? We didn't necessarily do anything wrong in the way that our process is built. We just haven't trained it yet. Does that answer your question, Brandon?
Yeah, I'm just a little surprised that even with all the computation that's currently happening, it's still as inaccurate as it is. But I guess the same could be said for how accurate it is already. I guess depending on the glass is half full mindset.
There you go. Yeah. So if we, oh, I see a question from Gary. Go ahead.
Yeah, so the loss after the epic, that's describing the like how true something is. Like you said, the closer to 1, it's like true, and closer to 0, it's essentially false. And then the actual accuracy is only 58% at the bottom. Am I hearing that right?
Yes, that's correct. So it's only accurate 58% of the time, and the output of my model is losing 0.67 every time it runs through. So it's further away from the optimal minimum at 0.67. Right. So
what is the loss again? It's just the can you go through what the loss is real quick?
Yeah, definitely. So our loss that we're utilizing the binary cross entropy loss to be able to calculate the loss. The loss is essentially taking the label, and it's not necessarily doing a subtraction. There's quite a bit of math that happens under the hood. But what it's trying to do is it's trying to identify, well, how much of a change do I need to make in order for the output to actually turn into the label, right? Our labels are coming in as ones and zeros, whereas our outputs from our model are coming out as 0.5s, 0.4s, 0.3s. They're not solid numbers, right? So our loss function is expected to be I don't ever expect to see our loss to be a definitive zero, right? And you should never expect that. If you see your loss be a definite zero, then likely your model has memorized data rather than actually learned. You do not want a definite zero in your loss function, right? And then your loss would work backwards through the backpropagation step to update each layer's weights and biases so that the next iteration that goes around, this loss functionality or this operation will be lower, or at least that's the hopes, right? And you shouldn't expect that loss to just be a continuous downward slope. You should instead expect it to be more of a random spikes with a slow, very slow decrease. Does that make sense?
Yeah, so you're saying the labels are 1 and 0, right? So like definite, like true or false. The output is actually what you get from what the data set. And then the loss is just representing your distance from how true or false something is.
The loss is representing the distance between this 0.54, which is the output of my model, and the label. My accuracy is saying, hey, how often is this model accurate? So how often is it actually making good predictions?
Okay, I got you.
Awesome. All right. So let's see what happens. And I'm actually going to try to close a couple of windows here before I run this. And if you're on an older PC and you are trying to keep up with me, please do not execute this block of code that I'm about to execute because it's going to take a little bit of time. So I'm going to go ahead and rather than running 20 epochs, I'm going to run this through 1,000 epochs. And instead of printing every single one of these, I am only going to print this if epoch, and I'm going to run the percentage sign here of 100 is equal to 0. All right, so only if I'm at the 100th iteration, which we should see 10 of them, will this be printed. And apparently I forgot how to write Python. There you go. All right, so I'm going to clear all of my outputs. I'm going to restart my kernel, make it brand new, as if none of this was occupying any memory space. And I'm going to run it from the top. So running from the top, there you see data loader has been completed. It's made it down to my training loop. Here's a couple of loss functionalities, right? It's being printed at every 100 step. All right, so there you go. We see 61, 71, all the way down. It looks like the final epoch was a 61.9. And that gives me a little bit of a better visual of its downward slope. So that's good. And now my model is just a tiny bit more accurate than what it was before. It went from 0.58, I believe was what I had originally, to now being 59% more accurate. And that was after 1,000 epochs. All right. Tomorrow we'll go over into training this and changing our model a little bit in order to get a little bit better performance. But this is not something unexpected. I'm going to restart my kernel again. I am now changing my batch size to be of 32 rather than 16. Executing all of it one more time. So there we can see it building my epochs. right? And with batch sizes of 32, it still stayed at an accuracy of 59, almost 60% right there. Look at that, we were close. All right. And that is how you build your training model. Well, as of right now, we have our model in itself. We've gone over how to pre-process our data, clean it up so that it looks correctly. We covered how to turn it into Tensor datasets to allow for the training process to take place. We talked about our criterion, which is binary cross entropy loss. We talked about the optimizer that we're utilizing, which in this case, we're utilizing Atom. We talked about placing our model into training mode, iterating through a number of epochs, which are just training iterations, going through the batch of samples that is provided through the training loader, which in this case it's 32. We've gone over how to apply the backward step, which is happening here. This is our back propagation. And then we tell our optimizer to finally take a step. Finally, we covered accuracy, where our model goes into the evaluation mode, where it's no longer updating weights and biases. It is no longer updating any gradients, nor is it calculating gradients or taking them into consideration. It is simply feeding features straight into our model that we are then rounding to evaluate to be true or false, which is the same as 0 or 1, and then passing in our labels into the accuracy function so that we can finally get this print statement that tells us exactly how accurate and how often our model was actually correct. At this point, does anyone have any questions? I see a question from Erjan.
Yes. So how many training would be considered overtraining or like overfitting?
That's a great question. And we're going to go into accounting for overfitting tomorrow. Typically, what I would say that you could do is apply something called an early stop, right? And what the early stop will do, which we'll go over into tomorrow, is it has essentially a how do I explain it? It has a limit where it's going to recognize, hey, this was the point where I had the lowest amount of loss. Every time that the loss is over a certain percentage of the lowest amount that I recorded, I'm going to mark it. And after that specific event happens 5 or 6 times, I'm just going to stop the training loop because at this point, my model's not learning. It's overfitting. Does that answer your question?
Yes. Thank you.
Of course. All right. Any other questions? Okay. It doesn't seem like there are any other questions. There are some concepts that we can apply to make this more efficient so that we don't have to feed it through so many loops here, right? If I were to change this to be 2000 epochs, I will get a little bit of a better response, but nothing considerably crazy. Instead, what we're going to be going into tomorrow is applying activation functions within our hidden layers and something called a dropout method, as far as, hey, this neuron here should no longer be taken into consideration because they met a specific condition. But again, that's going to be a lesson that we cover tomorrow. Because from the looks of it, we are at the 2-hour mark as of today, and I'm sure everybody's tired of hearing my voice. All right, so now you can see that we ran it through a considerable amount of more epochs. We have it all the way down to 1,900 epochs, and at this point, we're in the 5 nines, all right? And now my model at 2,000 epochs is a consistent 60% accuracy. So we can see that the more I train it, the more accurate my model will become. And I think that goes back to your original question, Brandon, about, hey, is this okay? This is definitely okay. We're fixing it. Hopefully by tomorrow, we'll get it up to the 70% accuracy. But it is all about training. All right, does anyone have any questions over any of the topics that we covered today? Okay, doesn't look like we have any questions. Let me see the chat here. I see Erica is trying to help me out. Thank you, Erica. I really appreciate it. All right, let me go ahead and stop the recording at this point.